In order to design a solution, one must first understand the problem. The principal evidence of climate change is the accumulation of heat in the oceans. Recent data suggests the 1998 to 2012 warming trend is about 1/3 to 1/2 of the trend over the 1951 to 2012 period. The most likely cause of this so-called hiatus is the movement of surface heat to deeper water. This climate hiatus evidences a practical solution to the problem. Ocean thermal energy conversion, or OTEC, converts surface heat to electrical energy by conveying the surface heat to the cold reservoir of the deep ocean through a heat engine. In the process of producing this energy, about 20 times more heat has to be moved to the cold sink in view of the low thermodynamic efficiency of the process. It is the sequestration of this heat, as well as the conversion of heat to work, that would produce the climate benefits scientists are only now recognizing. The slowdown in warming caused by the movement of heat to the deep over the past 15 years has caused problems for the IPCC as it releases its 5th assessment report, but is strong evidence of how mankind should approach the energy/environment question. The main issue with OTEC is the masses of water that must be processed due to the low thermodynamic efficiency of the process. This necessitates large infrastructure to get a reasonable power return, and with mass comes cost. Such movements impact marine life, have the potential to affect the thermohaline circulation that influences global climate patterns, and can release carbon dioxide dissolved in deep water when it is brought near the surface. The answer to these problems is to move the heat between hot and cold reservoirs via the phase changes of a working fluid rather than through massive water movements. It is the design and costing of such a system that is herein proposed. The first criterion is to select the working fluid. Each fluid has its own liquid density, latent heat, specific heat, and vapor density. The default velocity the vapor moves through a 1 meter cross-sectional pipe is 75 meters per second. The next criteria is to select the condenser material. The default size of the vapor channel is 2 meters for a cross-sectional area of 3.14 square meters, and the break tank is the outer area where the condensed vapor is returned to the surface. Its area is 1/4 the cross-section of the vapor channel. Each condenser material has its own density, thermal conductivity, and strength relative to steel. The latter is required to calculate the thickness of the pipe required to withstand the crushing force of 100 atmospheres pressing on the pipe at a depth of 1,000 meters. A steel pipe requires a wall thickness to radius ratio of 1 to 25 at a depth of 1,000 meters. Aluminum has to be 50% thicker. The next criteria is the temperature of the water at depth and at the surface, the plant efficiency, and the amount of power you want the plant to nominally produce. Due to OTEC's low thermodynamic efficiency, a great deal more heat than nominal energy has to be moved. The pressure of the vapor in the working channel, which is 4 times the area of the channel that returns the condensed fluid, acts like a manometer to help return the fluid to the surface. In this example, it raises the fluid 137 meters, leaving a head of 863 meters that has to be pumped. The cycle calculator is adapted from a postgraduate project of a group of Strathclyde University engineers in Scotland. The enthalpy and entropy data used in this calculator come from the Engineering Toolbox website. The preliminary condenser computation requires the confirmation of the vapor channel diameter, the vapor channel length, and the brake tank length. The brake tank length is the length of the brake tank exposed to the cooling waters of the ocean below the thermocline. The global warming mitigation approach to OTEC requires the recycling of as much heat as possible to the ocean's surface to maximize the amount of energy the ocean is able to produce and to limit the impact of OTEC production on the thermohaline circulation. To accomplish this, the condensed working fluid acts to condense a portion of the descending vapor in the condenser. In order to do this, the fluid must be cooled in a fluid condensing heat exchanger with deep ocean water circulating as the coolant. The formulas used to calculate the countercurrent effect are given here. More heat is returned to the surface as a result of the countercurrent circulation between the descending vapor and the working fluid rising in the brake tanks. The program calculates the dimensions of the condenser and the evaporator. It then produces a block diagram of the plant showing the calculated parameters. The brake tank, condenser, and fluid heat exchanger will be made from the same material as the vapor pipe. The return pipe's evaporator and platform may be manufactured of different material. This form allows you to input these materials, the thickness required, the number of pumps required, the weight of the pumps and the power set, and calculates the mass and displacement of the equipment. You are then directed to the bill of materials. The bill of materials cost of materials assumes a labor cost equal to the cost of materials and compares the total cost to a comparable nuclear power plant, which is the Vogtle plant in Georgia, with a combined rating of 2,400 megawatts and a cost of $8.87 billion. This cost is subject to the choice of materials and assumptions made in the program, but are sufficiently accurate to imply that such a system can be cost competitive with nuclear power within a reasonable development period. Some claim OTEC cannot be cost competitive because the energy is produced far offshore. The most rapidly expanding market for energy is Asia. As can be seen from this map, OTEC generated power is the nearest source of energy to the Asian market. Besides being emissions-free, it will relieve its customers of the pollutants that now plague them. Furthermore, hydrocarbons are becoming increasingly expensive as they get harder to access, while renewables become cheaper with experience and economies of scale.